You ever look up at the night sky and feel that tug of curiosity about our place in it all?
Hmm.
Maybe even about our own star, the sun, like where did it come from? Does it have family out there?
Right.
Well, if that sparks something in you, then you're in for a treat, because in this deep dive, we're kind of embarking on a cosmic family reunion.
That's a great way to put it.
We're going way back to the sun's birth, exploring who its siblings might be and, well, what secrets they could hold.
Exactly. Think of it like tracing the sun's family tree back billions of years, back to a time when it probably wasn't the solo star we see now.
Ah, so it's part of a crowd.
Likely, yeah, part of a bustling stellar nursery.
And to, dig into these connections, we've looked at some really fascinating research,
Yeah.
stuff exploring these ideas of solar siblings, stars born from the same cloud.
Correct.
They're almost identical solar twins, and even solar analogs, which sort of give us glimpses into the sun's past and future.
And technology is helping here, right?
Right.
I hear Gaia mentioned a lot. Oh, absolutely. Missions like Gaia are total game changers. The data is just incredible, fundamentally changing how we map out our galaxy and search for these connections.
Okay, so for you, the listener, our mission today is basically this. Why are scientists so interested in finding the sun's siblings? What are they actually looking for?
Mm.
What clues are out there?
Mm.
And maybe the biggest question, what could finding them tell us about, well, us, our solar system, maybe even life somewhere else?
It really starts with a core idea. Most stars, and that includes our sun, they don't just pop into existence alone. They form inside these huge clouds of gas and dust.
The
Yep.
molecular clouds.
Right, the stellar nurseries.
Exactly. And these births, they happen in crowds, big star clusters, sometimes with thousands of baby stars back together.
So the sun probably wasn't a cosmic lone wolf from day one. There's actual evidence suggesting it had company.
Precisely. And there are a couple of pretty intriguing clues in our own backyard, so to
Oh.
speak.
Like what? Well, one is the edge of our solar system. Out past Neptune, around 30 astronomical units or so, it seems to end quite sharply.
Sharply, what does that mean?
Well, some scientists think that this edge might have been kind of sculpted, trimmed maybe, by gravity from other stars passing nearby when the sun was young and still in that crowded cluster. It could have sort of sheared off the outer parts of the original gas and dust disk.
Huh. Like cosmic pruning shears shaping our system? That's quite an image. What's the other hint?
The other clue comes from the Kuiper belt, that icy zone out beyond Neptune. Some objects there have really weird orbits.
Weird how?
They're very stretched out, eccentric is the technical term, and they're often tilted way off from the main plane where the planets orbit.
Oh.
These odd paths could be leftover scars from a close brush with another star way back in the sun's infancy. And an encounter like that, much more likely if you're packed into a dense star cluster.
Right. More chance to bump into your neighbors.
Hmm.
So, okay, if the sun did have these siblings, this early entourage,
Hmm.
where did they all go?
Ah, yes, that is the multi-billion-year question, isn't it?
Yeah.
Over cosmic time, the galaxy's gravity, just the general churn of the Milky Way, it tends to pull these birth clusters apart.
So they just drifted.
Pretty much. The individual stars, the sun's siblings included, they all set off on their own unique orbits around the galactic center. So our challenge now is spotting them again, picking them out from, the hundreds of billions of other stars.
And that's where knowing the difference between twins, analogs, and siblings comes in handy for the search.
Exactly. They're related concepts, but distinct. Helps us refine what we're looking for.
Okay, let's break that down for you, the listener. Solar twin, solar analog, solar sibling, what's the difference?
Okay, think of it like degrees of family resemblance. Solar twins are the closest relatives, almost like stellar identical twins.
Identical how?
The definition is really strict. They have to be virtually indistinguishable from our sun in pretty much all the key ways. Mass, age, brightness, or luminosity, their exact chemical fingerprint, surface temperature, surface gravity, even down to things like magnetic activity.
Wow, a near-perfect copy.
Hmm.
Why is finding those so important?
Well, for a couple of really big reasons. First, if a star is basically the sun's double, there's a much higher chance it could host planets similar to ours.
Ah, an Earth-like planet around a sun-like star.
Exactly. And maybe, just maybe, if the conditions line up, it could support life based on the same stuff we know, carbon chemistry, liquid water.
So solar twins are prime real estate in the search for extraterrestrial life.
You could say that, yeah. The hunt for them really kicked off seriously back in the late 70s. A guy named Hardorp did some early work looking at star spectra, but didn't find any perfect matches back then.
Okay.
But later, data from the Hipparco satellite in the 90s, which was much more precise, helped identify a couple of really good candidates. Stars called Atin Scorpii, that's HIP 79672 and HIP 78399.
Any others?
Yeah, there's one called HD 186427, which is super interesting because we know it has planets, and it's remarkably sun-like in many ways.
But it sounds like finding these true twins is incredibly hard. You said only about a dozen possibles nearby.
That's right, the checklist is just really, really demanding.
Okay, so that's twins. What about solar analogs?
Right, analogs are a bit broader. They might not be identical to the sun right now, but they're stars that either looked very similar to our sun in the past, or they will look very similar in the future. Remember, stars change over their lifetimes.
Ah, so they're like peeking into the sun's photo album, seeing its past and future.
That's a perfect analogy. Studying analogs helps us understand the sun's own story. What was it like billions of years ago when life first got going on Earth? And what's going to happen to it billions of years down the road?
Cool. Provides context. Okay, now the main event for today. Solar siblings. How are they defined? What makes them siblings?
So, unlike twins, siblings don't necessarily have to look exactly like the sun today. Their temperature or brightness could be different. The defining feature, the absolute key, is their shared origin.
Meaning,
They must have formed at the same time as the sun, and crucially, from the very same initial cloud of gas and dust.
the same nursery.
Exactly. That shared birth certificate means they should have practically identical ages and, really importantly, the same basic chemical composition.
So the same cosmic DNA, even if they've grown up differently?
Precisely. And finding them, for you, the listener, this could be huge. It could help us figure out the specific environment where the sun was born. Did being in that cluster help or hinder the development of life here? Was being close to other young, active stars good or bad? We don't really know.
And you mentioned panspermia earlier.
Yeah.
This idea that life could hop between stars.
Yeah.
How do siblings fit into that?
Right, panspermia. It's the hypothesis that life isn't necessarily confined to one planet. It could be spread through space, maybe on rocks blasted off one world that land on another.
Like interplanetary seeds.
Kind of, yeah. Now, if the sun was born in a crowded cluster, its siblings would have been relatively close by for a while in the early days. So it raises this really wild possibility. Could life have started on, say, an early Earth, got knocked off into space on a rock, and then landed on a planet orbiting a sibling star? Or vice versa.
Whoa.
It means solar siblings could be prime targets if you're thinking about life potentially spreading between nearby young stars. Finding life on a sibling would be, well, game-changing for that idea.
Okay, mind officially blown on that one. Right, so we know what we're looking for, same age, same chemistry. But practically, how on earth do you sift through billions of stars to find them? Seems impossible.
It's definitely not easy. This is where galactic kinematics comes in.
Kinematics. Sounds like physics homework.
Sort of. It's basically the study of how stars move through the galaxy. Their speeds, the directions, the shapes of their orbits around the Milky Way's center. The thinking is, if siblings formed together with the sun and didn't get, violently kicked out of the cluster early on, they should still be traveling on broadly similar paths through the galaxy today.
So they might have drifted apart, but they're still following similar galactic traffic patterns.
That's a good way to think about it, yeah. They should have a similar sort of galactic address or commute route.
So scientists try to rewind their movements.
Kind of,
Yeah.
using really precise measurements of where stars are now and how they're moving, plus a model of how gravity works in the Milky Way. They try to calculate backward in time, see if different stars' paths might converge at a single point in the past.
That sounds incredibly complex. The galaxy isn't exactly simple.
Oh, it's hugely complex, and that was a major limitation. Before we had really good data, the estimates were pretty broad. Maybe 10 to 60 siblings lurking within about 300 light years or so.
But finding them just based on movement was tough.
Very tough. Our models of the galaxy's gravity, the pull of spiral arms, dark matter, giant molecular they weren't
Yeah.
perfect. Lots of uncertainties. It became clear you really needed super accurate ages and those chemical fingerprints too, not just the motion.
Right. You needed more pieces of the puzzle. And then Gaia.
And then Gaia, yes. It's been absolutely revolutionary for this field.
How so? What did Gaia bring to the table?
Its second big data release, Gaia DR2, was a watershed moment. It gave us these incredibly precise positions and motions astrometry, it's called, for well over 1 billion stars.
1 billion.
Yep. That massive leap in data quality just dramatically sharpened our ability to pick out potential sibling candidates from the crowd.
Okay, so tell us about some of the actual research using this Gaia data. Who's been finding what?
Well, one really key study came out in 2018, led by Atabekian. They started with this huge library of star spectra, like 17,000 of them,
Okay.
and they filtered them down, looking only for stars with chemistry extremely close to the sun's overall metallicity, the amount of elements heavier than hydrogen and helium.
Right, the basic chemical match first.
Exactly. Then they got even stricter, looking at the abundances of other specific elements and also comparing estimated ages. They whittled it down to just four main contenders.
Only 4. Wow.
Yeah, and even more amazingly, for two of those four, even the ratio of different carbon isotopes like carbon-12 versus carbon-13 matched the sun's ratio.
That's specific. That's like a really detailed DNA match.
It really is. It tells you not just that they formed together, but gives clues about the exact mix of materials available in that specific corner of the nebula where our solar system was born. It's insight we can't really get any other way.
Incredible. So how did they check the movements of these 4 stars? Did they try the rewinding thing?
Given how tricky rewinding orbits perfectly over billions of years is, they used a slightly different approach. They plotted the stars on something called a tumor diagram.
A tumor diagram. What's that?
It's a way of looking at a star's motion within the galaxy, but focusing on its overall velocity components, how fast it's moving rotationally around the galaxy versus how much it's moving radially and out and vertically up-down.
So it captures the traffic pattern idea.
Exactly. Stars born together should cluster together on this kind of diagram even after drifting apart. Based on the chemical match, the age match, and where they sat on the tumor diagram, they singled out one star, HD 1E6302, as their strongest candidate for a solar sibling.
HD 1E6302. Okay, one very strong lead. What about that other study you mentioned by Webb and colleagues in 2020? Did they take a different angle?
They did, yeah. Their focus was much more heavily on the kinematics, the motion. They used a different big data set, the SDSS APOG survey, over 19,000 stars with really good spectra, all selected to have iron levels very close to the sun's, and they combined that with the Gaia DR2 position and motion data.
So good chemistry info plus great motion info. What was their method?
They took a modeling approach. They basically simulated a star cluster dissolving over billions of years within different computer models of the Milky Way.
Different models.
Yeah, like a simple smooth galaxy, one with a central bar like ours has, and one with a bar and spiral arms, trying to account for those complexities we talked about.
Okay, so trying to make the simulation more realistic.
Right. First, they ran the sun's orbit backward in time in these models to estimate where it might have started. Then, they put a simulated cluster there and ran the clock forward.
Watching the simulated cluster spread out.
Exactly. And as the simulated stars spread, they calculated these things called orbital actions.
Orbital actions, what are those?
They're like fundamental quantities that describe an orbit how much energy it has in moving radially, rotationally, and vertically. The neat thing is, these actions tend to stay pretty constant over long periods, even as the star moves around. They're like a more stable, dynamical fingerprint than just position and velocity at one moment.
A more robust way to compare orbits over time.
Precisely. So they looked for stars in their real catalog, the apogee Gaia stars, whose calculated orbital actions closely match the sun's actions over the simulated 5 billion years.
And did they find matches?
They did. Despite all the uncertainties in galactic modeling, they ended up with a list of just over 100 primary candidates based on this dynamical matching.
100. That's more than 4.
It is, yeah, but based on a different primary criterion, the dynamics. Interestingly, some candidates that had popped up in earlier studies also made their list, which is encouraging.
Did they confirm or deny any previous ideas?
Yeah, their analysis pretty strongly suggested that a well-known nearby star cluster called M67 is not the sun's birth cluster, which had been a possibility people considered.
Okay, good to rule things out too. Who was their top candidate dynamically?
Their number one pick, which they called Solar Sibling 1, is currently about 360 parsecs away. That's a bit over 1,100 light years. Their simulations showed its orbital history, its dynamical journey, was remarkably similar to the sun's, even factoring in the galaxy's bar and spiral arms.
So different studies, different methods, but both pointing toward specific candidates. It really feels like we're closing in, doesn't it?
It really does. It's this amazing synergy, you know? You've got the incredible precision from Gaia, these huge spectroscopic surveys giving chemical details, and then increasingly sophisticated ways to model and analyze all that data. It's a massive cosmic puzzle, but yeah, the pieces are definitely starting to fit together.
Okay, let's try and wrap this up for you, the listener. What are the big takeaways from this deep dive into hunting for the sun's family?
I think the main points are the sun almost certainly wasn't born alone, it came from a cluster. Finding its siblings means looking for stars with the same birthday and the same basic chemistry that shared cosmic DNA.
Right.
We also touched on solar twins, the near perfect copies, and solar analogs, glimpses into the sun's past and future. Finding siblings involves studying how stars move, their galactic kinematics, and that's where Gaia has been absolutely key.
Yeah, the data is crucial.
Totally. And these latest studies, combining the chemistry and the detailed orbital modeling, are now giving us actual names like HD 186302 and Solar Sibling 1 as really promising candidates.
And for you listening, why does finding these stellar relatives actually matter? What's the payoff?
Well, figuring out where the sun was born tells us so much about how our own solar system formed and evolved early on. Did that cluster environment shape our planets? Did it affect how life got started here on Earth? Those are fundamental questions.
Hmm.
And then there's that wild panspermia idea. If siblings were close early on, could life have spread between them? Finding siblings, maybe one day finding planets around them, it connects directly to the search for life elsewhere.
So as we maybe get closer to actually identifying members of the sun's long-lost family, it really makes you wonder, doesn't it? What other secrets about our cosmic origins are tied up in that story? Could the sun's birth environment, that cluster, have played some crucial, maybe totally unexpected role in making Earth habitable?
It's a profound possibility.
Yep. Definitely something to think about next time you look up. But thanks for joining us on this deep dive.